Hello, it's me, Oscar from Marijuana Garden.
That's an exciting breakthrough. Based on your description, you're likely referring to the record-setting aluminum ion optical lattice clock, developed by researchers at the National Institute of Standards and Technology in the USA. Here's a detailed breakdown. Unprecedented precision and stability, accuracy, operates at optical frequencies, 1.12 petahertz, or 1.12 times 10 to the power of 15 hertz, far higher than traditional microwave cesium clocks. Systematic uncertainty. Achieved systematic uncertainty below 10 to the power of negative 19 parts in 10 quintillion. This is the 19 decimal precision. Stability reaches stability levels near 10 to the power of negative 18 after just seconds of averaging. This means its ticking is incredibly consistent over time. 1 second in 30 billion years. This translates its accuracy and stability. The age of the universe is approximately 13.8 billion years, so this clock would theoretically be less than 1 second off since the Big Bang. So here's how it works in a simplified way. First, a single positively charged aluminum ion, that's Al+, is trapped using electromagnetic fields inside an ultra-high vacuum chamber. This setup isolates the ion from pretty much all external disturbances. Then lasers are used to cool the ion down to nearly absolute zero, which in turn really minimizes any motion-induced errors. The so-called clock transition involves tuning a highly stable laser to a very specific ultra-narrow energy transition within the aluminum ion, specifically between the energy levels 3p0 and 3p1. This transition frequency basically acts as the pendulum swing of the clock. Now for quantum logic, a co-trapped magnesium ion, or Mg+, serves as a logic ion. Lasers are used to manipulate the magnesium ion to cool the aluminum ion even further, and to detect whether the aluminum ion absorbed the clock laser light, which tells us if the transition actually occurred. This clever technique allows us to avoid disturbing the aluminum ion directly during measurement. The frequency of the laser that's driving the aluminum ion transition is constantly measured and stabilized against this atomic reference. So why aluminum? So one of the remarkable things about the specific clock transition in aluminum ions is that it's exceptionally insensitive to external disturbances, like electromagnetic fields and temperature changes. This is actually a really big deal because it helps keep systematic uncertainty super low, and since the optical frequency is extremely high, it allows for much finer division of time, leading to even greater precision. Now let's talk about the groundbreaking implications for fundamental physics. With these clocks, we can test Einstein's theories of relativity by detecting incredibly tiny variations in the flow of time. Whether it's due to gravity, as described by general relativity, or motion, as in special relativity, the sensitivity here is just unprecedented. And who knows, this could even reveal deviations from Einstein's predictions, or provide evidence for entirely new physics. Another exciting application is searching for changes over time in fundamental constants, like the fine structure constant or the electron-to-proton mass ratio. If we ever found such variations, it would absolutely revolutionize our understanding of physics. Plus, these ultra-precise clocks can act as sensors for exotic things like dark matter fields or low-frequency gravitational waves. By detecting subtle changes in their tick rates when they're separated in space, they could give us clues about phenomena we've never been able to observe before. So, redefining the second is actually a pretty fascinating process. Right now, the international standard for a second is defined by cesium microwave transitions. But things are changing quickly. Optical clocks like this aluminum ion clock are actually the leading candidates to redefine the second. This time using optical frequencies. And honestly, that's expected to happen within this decade. Now let's talk about some of the advanced technologies making all this possible. Next-generation GNSS, like GPS and Galileo, are set to enable centimeter or even millimeter level global positioning. And get this, all without needing constant ground corrections. When it comes to ultra-precise Earth science, these advancements allow us to monitor tiny crustal movements, track sea level changes, and observe variations in Earth's gravitational field with unmatched accuracy. Deep space navigation will soon allow for autonomous, highly precise navigation for spacecraft exploring the solar system and beyond. And looking ahead, quantum networks and computing are expected to serve as critical nodes for synchronizing future large-scale quantum communication networks and computers. So, where are we now? Well, these clocks are still lab-bound, meaning they're currently complex, large, and require significant infrastructure and expert operation. They're definitely not portable yet. Demonstrating their stability over long distances via optical fiber links is super important for practical applications and, honestly, for redefining the second itself. Networks of these clocks are actively being built, and while aluminum ion holds the accuracy record, other optical clocks, using strontium, ytterbium, strontium in lattices, or even highly charged ions, are also incredibly advanced and offer different advantages like the potential for portability. In essence, the NIST Aluminum Ion Clock represents the pinnacle of human timekeeping. Its mind-boggling precision isn't just about telling time better, it's truly a revolutionary scientific instrument poised to probe the deepest questions about the universe's fundamental laws and enable technologies we can barely imagine today. It really does redefine the meaning of precision measurement.
Thank you.